Hello gems, welcome back to another video. This is the ultimate grind for BITSAT 2025. This is the question bank series, and with every episode of this series we are getting 10 questions stronger in every chapter for BITSAT 2025. Okay, so today we are discussing the chapter of current electricity. So previously we have discussed all the 11 standard chapters and the 12 standard chapters that come before this. So if you have missed out on those, the full playlist will be available in the description box of this video. Okay, you can check it out once you finish with this one. Okay, so the trend is we study the previous year trends, we see which topics are being important, and we pick out certain topics and practice questions from those topics. Okay, so the motto of this series is to give you that boost, that relevant source of questions, so that you get stronger in those particular topics that will be relevant for your exam. Okay, so that is the motto of the series. So as to provide you with the relevant questions that will help you directly in your exams. Okay, so if you connect with this motive of collecting this important questions and cracking your exam, do consider subscribing, and in March we'll bring up the strategy for BITSAT 2025 as requested by many of you. So we'll bring up the complete strategy. We don't have a lot with us, we don't have 12 months, but we have 12 weeks, right? And a lot can be done in 12 weeks, and we'll build up on that in the strategy video. So for now, let's begin with today's video, wherein we'll be getting 10 questions stronger in the chapter of current and electricity. Question 1 and 2 over here. So question 1 is based on mobility. Okay, you are supposed to find the mobility. You are given the drift velocity and the electric field. This is a simple formula. You'll also find it in your NCERT. Mobility is defined as Vd by E. Okay, the drift velocity by the electric field. Okay, so more drift velocity, basically more mobile will be the charges, right, for a given field, of course. So Vd is, if you see, 7.5 into 10 to the power minus 4, and so you are supposed to provide the answer in the same units, so let's not worry about the units, and 3 into 10 to the power minus 10. So this will be 10 to the power 6, right? This will go on top as plus 10 minus 4, so plus 6, and 3 2s are and 3 5s are, right? So that is simple math, 2.5 into 10 to the power 6. So option A is correct. Okay, based on a simple formula we have a simple question. So let's come to question 2. Here we have the resistance of a wire being given as R ohms. If it's melted and it's stretched to n times its original length, okay, the new resistance will be, okay, it won't be n times R. You might think that since length is done n times L, right, new length is n times the previous length, so you might think that resistance is proportional to length, and directly you can say it is n times R. But here you can see that it is melted and then it is stretched, right? When you stretch a wire, of course its length will increase, but the area is decreasing, right? So what is remaining constant? Volume, right? So volume of the first wire in the first case is equal to the volume in the second case. So the volume is remaining constant. It's the wire will occupy same amount, okay, the same amount of space, that is volume. So volume is remaining constant. You can imagine it. So yeah, if you have a wire this big, so when you stretch it, its length is broadening, but the cross section area will decrease, right? So the length is broadening at the cost of cross section area. Okay, so the area is also decreasing and length is increasing. So resistance will increase more, right? Not just n times. Okay, so let us say this from this equation we can find. So about length, you know, so this is the second case length, right? It becomes n times L. What happens to the area? So we can write A1 L1 is equal to A2 L2, right? Our question is what happens to area, okay, when length increases by n times L. So initial area, let's suppose it is A, initial length L, final area A2, this is what we are supposed to find. Final length n times L, right? Final length is n times L. So this and this can get cancelled. You'll see that area in the second case will be area by n, right? And of course it will decrease, right? The length is increased at the cost of cross sectional area. You can picture that. So R, new R will be rho L dash or L2 and A2 I use. So R2 in the second case. So rho, anyways, it is rho is going to remain the same. The material is not changed. The wire is itself melted and stretched, right? So now L2 is n times of L. Area becomes A by n, right? So this n will go on top and we'll have n square times rho L by A. Now what is this? This is the previous resistance, right? Previously the wire had length L and area A. So this is the original resistance R1, you can see, or R as they have given in the question. So n square times R. Okay, so don't think linear. When you stretch the wire, you will increase the area, you'll increase the length, of course, but you'll also decrease the area by n, okay, by that fraction, and you increase the length by that times. Okay, so that leads to a fraction, to a value of n square times R. So that's about these two questions. Over to the next one. Let's discuss question 3 and 4 over here. We are supposed to find R equivalent between A and B. Okay, so this type of questions, I recommend you to simplify the circuit, right? It's very simple when you simplify it. Okay, that's 2024 gem of physics. Okay, water quote. It's very simple when you simplify it. Wow. So if you go by this, so wherever there is just wire, you maintain the same potential, right? So suppose the potential over here is A, so here also it will be A, no resistor, no capacitor, nothing in between. So here also it will be A, here also it will be B, and here, so B, 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 no potential drop, right? So if this point is B, it is same as saying if you connect it by the wire, so same potential will be the same. So you can call this point also B, this point also B, okay? So we'll see why we are doing this. So we'll call this point C, since this and this point is connected by a resistor, right? Here also you'll see there is some resistor, so there will be some voltage drop. Now you cannot say this is B and this is B, or this is A and this is A, because there is a resistor, right? There is some potential drop, so potential has changed. Okay, so similarly this point will be C. Okay, so now let us draw the points across which we are supposed to find the potential, A and B. Now C, you can draw it anywhere, so let's draw it in between. Okay, so now you'll see this circuit boils down to something very simple, okay, which you'll be able to solve just within a few seconds. Okay, so if you see this resistor, okay, let's see each resistor where it is connected. If you see this resistor, it is connected between A and C. Okay, so this we have counted. If you see this one, it is between B and C. Okay, this is counted. Let's come to this one. What is this? So this is point A, this is point A, this is also point A. Okay, this is point B, point B, point B. Right? So this is between A and C. Okay, this is connected, right? So A and C again. Okay, so if you see this and this are in parallel, it was so hard to see just like that, right? So if you see this one and this one will be in parallel. Now if you see, it's between B and C, B and C, right? So here we have between B and C. Okay. So so this is done. This is done. Only with this one we have, which is between A and B. Right. So we can draw it like this. So each one has value R, 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 where R is 2. Okay. Now R and R in parallel. So 2 and 2 in parallel will be 1. Right. So if you have R and R in parallel, basically it becomes half. Okay, 2 and 2 in parallel, half of that 1, right? So this will become 1, this will become 1, and we have 2 in parallel, right? This 1 and 1 will be in series, so this will be 1 plus 1, 2, and again you have parallel with 2, right? Not equal to, this is parallel with 2, right? This 2, 2, 1, 2, 2, 1, add them because they are in series, so that is 2. So in this branch we have 2, and here also we have 2. Right, so 2 and 2 in parallel, so 2 and 2 in parallel, we have 1, right? Just now I told you R and R in parallel gives you R by 2. So 2 and 2 in parallel, half of that 1. Okay, so the correct answer over here is 1. That is your equivalent resistance. Okay, we didn't do it by using any formula. Okay, that was the trick. R and R in parallel gives you R by 2. Okay, you can use the formula, you'll end up at the same answer. Okay, so let's come to this one. Here we are given a voltmeter. We are supposed to tell its reading, and note that it has some resistance. Okay, it's not a ideal voltmeter. If it was ideal, you just forget about it, find the equivalent resistance, and then find the voltage. Right, V is equal to IR, and it is very simple. But here the voltmeter also has some finite voltage, okay, which will contribute. You see this and this are comparable, right? It's not very high, so that very less current will flow, but if you see this and this is very comparative, right? 600 and double of that, okay? It's comparable. So there will be some current also flowing in the voltmeter branch, okay, and that will lead to some different value, right? So let us solve this circuit. So we'll replace voltmeter by 1200 ohms, and here we'll have 600 ohms and 400 ohms. Okay, so we'll treat it as a resistor for the time being to find R equivalent and to find the current in the circuit. Okay, so what is the current? So then we can find the voltage, right? So this and this in parallel. Okay, so now one more trick I can give you. 2R and R in parallel gives you the bigger value by 3. Okay, 2R and R. So 2 times this is in parallel. So you take the bigger value divided by 3. Okay, R and 2R. So 600 2 is 1200, right? So that will give you 1200. So the bigger value divided by 3. And you have R and 2R in parallel. Okay, that is the key to know. Just don't apply it anywhere. Okay, so 3 4s are. So we have 400, right? Or you can do it in your formula also. R equivalent, you will know that R1 into R2 by R1 plus R2. This will be way too much, but you see 1200, 600 divided by 600 plus 1200, so 1800, this and this and this and this cancels. Okay, 6 3s are 18, okay, and 3 4s are 12, and this is 100, right? So 400. So okay, this is 400 plus 400, okay, 400 plus 400, which is 800. So I will be V by R equivalent, right? Our objective was to find the current first, then we'll go for voltage. So V by R equivalent. So what is V? V is 10. So 10 voltage is divided among 800 ohms. Okay, we're doing things correctly. Fine. So sorry. So 10. So 1 by 80. That is what we get. Okay, let's find the voltage. Okay, so what we'll do now, this 10 volt is split among this and this, right? So the voltage across this resistor will be the same as across the voltmeter, right? As both are in parallel. In parallel, voltage remains same. So what we'll do, we'll find the voltage across this 400 ohm resistor and subtract it from 10, right? Because total voltage 10 is split among this. So we'll find the voltage across this minus 10, that will be the voltage over here. Okay, so I hope the idea is clear. So we'll find the voltage across the 400 ohm resistor. So that will be I into R, right? So I is 1 by 80, that is the current which is flowing in the circuit, times the resistance, which is 400. So this and this cancels. 8 5s are 40. So 5 volts across this resistor, and what is remaining? 10 minus 5, 5 volts. 5 volts across this resistor. Okay, so 5 volts is the correct choice over here, and it was very obvious, right? This is also 400, this is also 400. So if, the voltage would have split up equally, right? 400 400, so 5 and 5 volts. Okay, so that was the logic. Anyways, so that was your answer, 5 volts. Over to the next question. Question 5 and 6 over here. In question 5 we have a carbon resistance. Okay, so for this you are supposed to know what the colors mean. Okay, so you are supposed to find the resistance, right? The bands are given, the colors are given. So what is the way to remember it? B.B. Roy of Great Britain has a very good wife. Okay, no judging over here. So B.B. Roy. So first is the black one. Okay, please remember that this is black and it starts from 0. This is brown, and so this is 1. So we have brown over here. We have white. Okay, so B.B. Roy of we don't write it. B.B. Roy of Great Britain. So Great Britain has we don't write again. Very good wife. Very good wife. Okay, so what is this? White is at the very last, right? So 1 0 1 2 3 4 5 6 7 8 9. So this is 9. So white is 9. So you can directly see none of them have 9 in it except the D option. So this is the correct choice. But let's get it in the entire sense. Okay, so now brown, I told you it is 1. Okay, there is no decimal over here. It's 91 plain. Then red is over here, right? BB Roy. So this is red. So what is this? This is 2, right? So this gives you the power. Okay, so the third color will give you the power, 10 to the power. This 2 will give you the first 2 digits, no decimal between them. Okay, once I made a mistake for exam. So there is no decimal between them, and times this third color will give you 10 to the power. Okay, if you want the other colors, this is orange, this is yellow, okay, this is green, this is blue, what is this? Violet. Okay, I'm unsure about that. I'm also. And this is gray, right? I remember gray is 8. Okay, gray is 8. Great. Okay, so that is how I remember this, because there is also this G, right? This stands for green. So green is basically 5 if I remember it correctly. So this is 3, it's 4, yeah. So gray is 8, so great. So that is how I remember this, and this is 6 and this is 7. Okay, so you can remember it that way. It's quite simple. B.B. Roy of Great Britain has very good way. Okay, let's come to question 6. Here we are given a Wheatstone network. So this when you're given certain this type of circuit, this should trigger your mind that this is a Wheatstone network, okay, a kite shape, and you have a resistor in between. The first thing that you're supposed to check is whether this balance out each other, right? What is the balancing condition? R1 by R2 is R3 by R4, right? So this by this, if this is equal to this by this, then this is a balanced Wheatstone network, and no current will flow through this branch. Okay, so you as well might neglect it. Okay, now the circuit will become simple. Okay, so let us check if it is balanced. If it's not, the process might get complicated. So R1 is 30 by R2 is 90. So what is this? So this cancels 3. 3 ones are 3 threes are, right? So this is 1 by 3. Then R3 by R4. So this by this, again if you see, it is 1/3, right? So R1 by R2, these are equal. Okay, so this is a balanced Wheatstone network. You can just forget about this resistor. Okay, so since no current is flowing through it, so we'll just forget about it. Now the circuit is very simple, right? These two are in series, these two are in series, and then they are in parallel, right? So again, you'll see the equivalent will come out to be the average. So 30 plus 10, they are in series, 40, and this plus this, that is 120. Okay, so these two are in parallel, right? So 40 parallel with, so this is 40, this is 120. So 40 parallel with 120. So what is that? Product upon sum. So 40. So this is 160, right? So this and this we can cancel. 4 4s, 4 3s, so 30. Right? So if it was R, basically the equivalent would have been R. Okay, but here there are different values, so you get 30. Okay, so now 30 ohm resistance, okay, and 40 volts, and this 10 volts is also there. So we have simplified the circuit. So it's simple when you simplify it. That's simple when you can simplify it. So this is the circuit now, 40 volts. Now again these two are in parallel? No, they are in series. Okay, same current is flowing through them, I, right? There is no branching, although they might seem in parallel, they are in series. Right? Same current is flowing. In parallel, the current splits. Okay, so that is a criteria that you should keep in mind. So 30 plus 10, so R equivalent final is 40. Right? 30 plus 10 is 40. So I will be V by R. So 40 by 40, which is 1 amperes. Okay, so option B is your correct choice. Okay, so I hope that is clear. Over to the next question. So question 7 and 8 over here. In question 7, we are given two battery arrangements, 18 volts and 12 volts. Now keep in mind they have internal resistance. One has 2 ohms and one has 1 ohm. Okay, so this might even not be shown in the question. Here I've shown, thanks to me, but please read the question carefully. Okay, so you might jump into the circuit directly, but here they have given the internal resistances, so you are supposed to consider that as well. Okay, they might not show it, okay, altogether. So here actually here this one has 2 ohm resistor, and this one has 1 ohm resistor, right? So that is the accurate picture over here. Okay, you are supposed to tell what are we supposed to tell. So what is the value of this V? Okay, that is what we are supposed to tell. So now let us consider this current in the circuit I. Okay, so it is going like this. Actually, it will be going like this, right? Because 18 volt is bigger than 12 volt, so current will be coming out from this battery and going into this battery. Now, nothing is given as such about this voltmeter, so we'll consider it to be ideal. So no resistance, sorry, very high resistance. So no current will go in that branch. The current will flow only like this in this particular loop. Okay, it won't go in that loop because the voltage for a voltmeter, the current is, sorry, the resistance is very high. So the current will not go in that particular branch. Okay, so now we can use KVL, we can use this A, B, I'll start naming from here, A, B, C, D. Okay, and the current coming, let us say, is I. Okay, and know where it is splitting, right? So let us start from A. So A, from A we are going to, so everywhere it is I. Okay. So from A we are going to B. So first of all we encounter this resistance. So the current is in this direction. We are also going in this direction. So in the direction of the current, the voltage is negative, right? Because in the current flows from higher potential to lower potential, right? So you go, there is a decrease in potential when you go along the direction of current. That is it's actually convention. Anyways, when you complete the loop, you put it equal to 0. So some people may take it other way around, but I like to take it this way, that when you are in the direction of the current, the voltage will be negative. There will be a voltage drop. So what will be the voltage drop? R times I, IR, right? So I times R. Okay, so minus 2I. Now we are going from lower potential to higher potential. So there is a gain. So plus AT. So A to B completed. Then we go B to C, wire, nothing happens. Then we have C to D. So firstly we have this battery. So we are going from higher potential to lower potential. So there is a drop in potential, minus 12. Okay, so you can see they are opposing each other's action, right? This is this way, this is that way. So they are cancelling out each other. Okay, so you could have directly solved it. Anyways, so now we are going from C to D. Current is also going with us, right? Current has this direction. We are also going in the direction of current. So R times I, that is the potential drop. Okay, so this is equal to 0. So that will give you the current, right? This will be minus 3I. This will be plus 6 is equal to 0. So I is equal to 3I is equal to 6. I is equal to 2. Right? Simple solving of linear equation. So current is 2. We are supposed to tell the voltage. What will be the voltage? You can find in any branch you can use. So from A to B, or you can also choose C to D. The physics remains the same. It won't lie. So let's go from A to B. So here we have, so A to B is this part, right? So it is 18 minus 2I. Now we have the value of I. So this will give you the voltage, right? So from here to here we are going. So that is what we want, the voltage across these 2 points. Okay, so which is 18 minus 2I. So 18 is 18 minus 2 times of I. 2 2s are 4. Okay, so that will be 14 volts, which is option A. Okay, so that is your correct answer. Let's come to this one. Here in this circuit, the power consumed is P. Okay, the power consumed in the given circuit is P on interchanging the position of 3 and 12. Okay, so you interchange this, what will be the power consumption? So the power consumption is actually P prime in that case when you interchange. So what is P prime by P? Okay, so first of all, what is P? Okay, we are supposed to find P and P prime, and then we can take the ratio, right? So first of all, let us find this P. How will we find P? We know that power is I square R, right? Or R equivalent we can use. Okay, I think we can use this formula for here. So we'll have to solve this circuit. Now I told you a trick for this. This is 3 and this is 2. 3 2s are 6. So you take the bigger one divided by 3. Right? Take the bigger one, and if you remember 2R and R, which is the 2R by 3. We do that, right? So 6 and 3 in parallel, if you can remember, it is 2 ohms. Okay. Some students directly remember this. 6 and 3 in parallel is 2 ohms. So now this 2 ohms is in series with 12. So finally you will have 14 ohm resistance. Okay, so that saved you a lot of calculations, right? So the R equivalent is nothing but 14 ohms. So I will be V by R, right? V by R. So what is the current? So again, 14 by 14, right? V by R. So it is 1 ampere. So 1 ampere current is coming out of the circuit. Okay, and the equivalent resistance is 14. So power will be I square R. So I square, 1 square is 1 and R is 14. So 14, P is 14. Okay, so this is what we have. P is 14. Now let us find P prime. We have to interchange this and that. So this is 6 ohms, this is 12 ohms. Now this is 3 ohms. Okay, we are interchanging the 3 ohms and the 12 ohms, right? So this is 14 again. Okay, now this is the circuit. Now this will give us P prime, right? So if you see 6 and 12, again 6 2s are is 12, right? So this is 2R over here. So 12 by 3 you can do. Okay, 2R by 3, that is the formula we are using. So 2R by 3 is 4. So this is 4 ohms. So this is 4 ohms and plus 3. 4 plus 3, 7. Okay, so that saved you a lot of calculation. So 7 and I will be V by R. So now V is 14 again and R is 7. So current will be 2 amperes. 14 by 7 is 2. So now we are supposed to find power, right? P dash will be I square R. I square is 2 square is 4 and that times 7 is 28, right? So even if you compare the current, if you see it is power is related to I square, right? So here the current becomes twice, right, of this value. So the power will become 4 times, okay, which is 28. Am I saying something wrong? What is R equivalent? Okay, R equivalent has also changed. Okay, just don't mind me saying that. Okay, just forget the previous few things that I said. It was something foolish. Anyways, so we found P dash and we found P. Okay, I didn't consider the fact that R equivalent was also changed. Okay, so that will be 28 by 14, which will give us option A as the correct choice, which is 2. Okay, so the ratio is 2. So that is how you do this question, quite straightforward. Okay, just simple formula and then solving the circuit, right? So let's move to the last set of questions now. 9 and 10 over here. Question 9, we have this circuit. We are supposed to find the current through this 5 ohm resistor, right? So you can use Kirchhoff's law. So for that you'll need current. You might draw it from the bigger cell, but that will make it complicated, right? That might, because this current will split over here. It will go in this battery and that battery. So the best thing is to split the current when you have cells like this. You split the current from the in between one and you split it between these two. Okay, that is something that will help you easily in this question. So I1 and I2. So I is coming from the 6 volt battery and it's splitting into I1 and I2. Okay, so I1 will go like this complete loop and I2 will complete this complete. Okay, so what we are supposed to find is I1, right? So let us find that. Okay, so first of all, let us start from here, right? So we'll consider one loop this and one this loop. Okay, so we'll start from here. So 6 volts, right? Then we have minus. Now we are moving. Now we'll say this is A, B, C. Okay, we are moving. So only one loop will be enough, I guess. Okay, so from A to B, we are moving from lower potential to higher potential. So plus, right? Plus 6 volts. Then we are moving in the direction of the current. So again, drop of voltage. So minus 5 times I1, I times R. Okay, then we are moving from lower potential to higher potential. So plus 8. Okay, so that will be equal to 0 because we have completed the loop. The voltage, sum of the voltages in a loop is 0, right? According to Kirchhoff's law. So phi I1 will be 8 plus 6, which is 14. I1 is 14 by 5, which is 2.8, right? By the way, there is a trick to divide by 5. You just multiply by 2. Okay, so that will be, so you basically multiply by 2 and shift the decimal, right? 14 to is 28 and shift the decimal, that is 2.8. Okay, so that is how you divide by 5. Okay, that's a short trick for you since you made it this far in the video. Okay, the logic is simple: 14 times 2 divided by 5 times 2. right? This is 28, this is 10, so just shifting the decimal, right? So multiply by 2, shift the decimal when you have divided by 5. Okay, so now final question for the day. Here we have a potentiometer of wire length L. Now this wire also has resistance R. Okay, now we have EMF, a cell that we are supposed to use E0, okay, to balance some other EMF. So this one has internal resistance of R1, okay, uh, and the other one that we are supposed to balance, it will have the same way. It should be positive to positive, right? And here we'll have the galvanometer, which will detect the current as 0 at the balancing point. Okay, so an unknown EMF is balanced. So at this, suppose L is the balancing point. So L is the balancing length of the potentiometer. So the total length is capital L, right? So total length is capital L, and it has resistance R. Okay, R ohm cell, right? So now you are supposed to tell what will be this EMF E, okay, in terms of this, all this. Okay, there were options, but I needed space. So let us solve this. It is not that difficult. So the concept is whatever the voltage is over here will be present over here, right? Because the EMF is connected to this wire, right? So the voltage drop across this will be the same as voltage drop across this and this cell. So there is some, and it is divided among the length. Okay, so we'll do it step by step. So what is the voltage drop over here? So it is E naught minus I times of R1. You can say the current flowing in this loop is I. Okay, is there current over here? No, right? Because at the balancing point this will be 0. So there is essentially no current as such over here. Okay, so the entire current is flowing like this. So this is the voltage across the wire, we can say, right? This is the voltage over here. So this is also the voltage across the wire, right? So this voltage is falling across length L, capital L, right? So this is the length of the wire. So phi, which is the voltage drop or gradient, sorry. So that will be V by L, okay, capital L, because this the entire voltage V is falling across length L. V is falling across length L, so V by L, right? So that is the voltage that is falling per unit length. Okay, so that is the gradient, right? That is the voltage per unit length. If you take that much voltage should fall, so that the entire voltage falls by length L. So that is the idea, okay, of gradient. Anyways, it is defined by V by L. Okay, so now this EMF is balanced by length L. Okay, now this EMF internal resistance, there is no such thing, but anyways the current is 0 over here. So EMF is balanced by length small l. Okay, so whatever voltage is across this, across small length L, is the voltage across this. Can I say that? Yes, right, because the current is 0, so voltage, there is no potential difference between these 2 points, right? That is what it means. Okay, so whatever voltage has dropped across this is essentially the voltage of this cell, right? Basically that is the concept of your potentiometer, right? So what is the voltage that has dropped across this? That is the question. So that will be also equal to E, right? E will be equal to the voltage drop across this length. So that is why we defined this phi, right? What is the voltage drop across this? You just multiply phi with L. Okay, phi with length, you multiply it by length, that will give you the voltage drop across that length, right? Because phi, total phi is voltage by length, right? So this amount of voltage has fallen across. If you see phi, even if you don't want the concept of phi at all, so the voltage drop across this wire is in length L, right? You want to find for length L what is the voltage drop. So what you do, crisscross, right? V L by capital L. V by L is phi, right? That is what I've written. Okay, phi times L, phi times L. Okay, so yeah, you can see it anyway. So now we'll write it as V by L, this, right? So what is V? V is E naught minus IR, right? This minus IR. So that times L by L. Okay, so of course the answers were not in terms of I, since I is something that we have defined. Okay, answer was in terms of R1, R, and E naught L and capital L. Okay, so how will we define I? So basically we have to substitute I. Okay, so I, if you see, it is the current in this part, right? In this loop, there is no current over here, so only the current over here. So simply you can see it is V by R, right? Whatever the voltage is divided by the resistance, because these two resistance are in series, okay? Because same current is flowing, right? There is no breaking of current, so that will mean parallel, but these two currents are in series. So voltage is E naught minus, okay, voltages again will reach like that, or I can use Kirchhoff's law. Yeah. Anyways, so I is dropped across this, right? R1 plus R. So this E naught will drop across R1 and R, right? So that is what I mean. So I will be E naught by R1 plus R. Okay, E is equal to IR hybrid. Okay, so this entire voltage will drop across this and also this wire. Okay, across this wire, that's why we have subtracted this value, right? So what is R1? R1 is the resistance over here, right? So this should have been R1. Yes. Okay. Yes. So now let us substitute that. So we have E is equal to E naught minus I. I is this thing, R1 plus R into L, and what do you have, by capital L, right? So if you see this one will come on top, this E naught R1 will cancel with this E naught R1, so you will be left with E naught R, resistance of the wire, L by R1 plus R2 capital L. Okay, so you have the same form, right? V by L when you, E by V when you have, it is basically you have small l by capital L. If you remember the NCRT formula, here it is, everything is ideal. This one does not have internal resistance. So now we have internal resistance, so there is this minus IR factor. Okay, if you didn't have that, you'll have the NCRT formula, right? But here we have that factor, so we have to find the R, and then you do simple math and you will get your answer. So that is your answer. This was the final answer mentioned in the R1 and R. So in the options. So that's about these two questions. I hope you really enjoyed today's session, and we'll continue with the series throughout BITSAT. We'll bring out some different content based on the strategy, and then we'll also bring out question bank. Sorry, not question bank. This is question bank. We'll do some mock tests for practice before BITSAT. So if you are interested in that, do consider subscribing. I'll see you soon in the next strategy video, and till then, keep enjoying physics.